Testing. I think we're good. Okay, so first of the things we're going to review and kind of go over in our leftovers lesson here is talking about titrations. Okay, you guys should know how to do two different types of titrations by now. There's the redox titration, which we did in our redox unit. The idea of using either potassium permanganate or probably some sort of dichromate, and it'll change color as it goes a redox reaction. But we can also talk about this when it comes to acids and bases again, right? Because the basic idea is that if I were to sketch a graph out, right, we did this in Chem 20. Let's see if this thing works good today. Imagine that I had a graph that started like this, kind of goes up like that, and goes like this. What are we doing here? Am I adding if this is pH here, and this is, say, volume of titrant. Am I adding an acid to a base or a base to an acid? Good, okay. Because we start off with acid and it's becoming more basic. Hopefully that's clear. And one of the things we talked about vocabulary-wise is that ideally we should have a pH change roughly about 7. That's what we're aiming for here. And we call that the endpoint. And the endpoint is distinguished by a color change. And so the labs we've done, usually what we try to do is we try to make it so that it goes from clear to pink or purple, something like that. And then as soon as it stays the lightest drop of purple, that's how you know when to stop. The other vocabulary word you guys should know then is the actual volume of titrant you used is called the equivalence point. It's not writing very good today. The equivalence point will always be in milliliters. Well, actually, I can't say it's always in milliliters, but it's probably in milliliters. And do you guys remember the rules for how many trials you need to have in order for it to be considered valid? 3 within 0.2. Yeah, I'll write that out here as well. You're looking for 3 trials within 0.2 milliliters of each other. And if you do that, that creates what we call a pH curve, or ideally somewhere in here is where we see that color change. The reason why is that phenolphthalein is probably the best one we use. Phenol, P-H-T-H-A-L-E-I-N, something like that. Phenolphthalein, I think, changes color from 8.2 to 10. Pardon me. And it goes from colorless to pink. So my goal today now is to kind of build on this concept a bit, because we've talked about pH curves before in like the grade 11 course, Chem 20. We're going to talk about it a bit some more now that we know a bit more about acids and bases. So before I kind of continue on with my notes, let's just review some concepts of acids and bases. What makes something considered strong? It's lack of desire to go back to where it started. That's what makes you strong. Stay strong. Don't get back together with your ex. Right? Silly, but it'll stick in your head, right? As A plus B tries to turn into C plus D, that is strong. The reason why it's strong is that it 100% reacted and had no desire to all of a sudden, oh, let's get back together again, right? That's what makes something strong. Okay. Well, when it comes to these pH curves and these graphs right here, we actually have to modify things. I actually was telling you lies when we did Chem 20. This graph right here is very specifically for when you start off with a strong acid, and what you're doing is you're adding a strong base to it. And that's how this graph looks. But I'm going to show you a little bit later today that what happens if we have weaker acids. Remember how weaker acids, they don't react quite as often. They try to react, and then they go right back to where they started. That's going to change how the graph looks. So why don't I start with this slide right here. This is what we would have done in Chem 20, this sort of picture here. And you guys can hopefully see that this time around we're doing the opposite. Now I am taking sodium hydroxide, and I'm titrating it with HCl. If you want to use the right vocabulary, the NaOH would be considered your sample, and your HCl would be considered your titrant. And you guys can see it has the curve that we're looking for. And more appropriately, it has that endpoint right at 7, which we kind of expect, because really what happens when an acid and a base react? What do you make? Water. And water's pH is? Yeah. But what happens if you're reacting not a strong acid or a strong base, but a weak acid? And remember, a weak acid is one where it tries to turn into hydronium, but then it goes right back again. Or if you use a weak base, it tries as well. And it kind of changes the way the graph looks here. Okay. I'm going to get to that in a bit. Let me go through the notes I have right here, because before I get there, one of my leftovers is to talk about something called a buffering region. Okay. This is a vocabulary I need you guys to know. There's almost always one question on the diploma about something called a buffer. And I understand you guys do a little bit of talk in biology about buffers. Is that right? You guys have heard this term before? So what is a buffer in biology terms that you guys have heard before? What can I build on here? What do you know about buffers? Okay, that'll work. I would change the definition slightly then. A buffer doesn't necessarily keep something neutral, but what it does do is it resists pH change. And so if you want it to stay neutral, that'll work. But let me go back to this picture right here. Can you guys see how right here they've labeled this section here as a buffering region? The reason why they call that a buffer is that the pH right here really didn't change all that much. Here it was 13.7, then it's 13.6, then it's 13.2, then it's 13. Can you see how right here the pH didn't really change all that much? We call that a buffer. Anytime a pH resists change. And there's a lot of places where you'd want to have a buffer. So am I in your way? I'm going to back up here. I feel like I'm in your way. For example, a good place for a buffer system would be in, did you guys mention blood? Is that the one that you talked about in bio? Yeah, blood. You want to maintain a very constant pH in your blood. Whether or not it happens to be at 8.0 or 3.2, I don't really know what the number is, but you'd want to maintain the same pH. Another really good example, a hot tub. Anybody have a hot tub? You have to like add chemicals and stuff like that to a regular basis, do any testing on it to make sure that like it maintains a pH, right? Swimming pools would be a good example. If they become either too acidic or too basic, then it's probably hazardous to our skin. So anyways, that's the terminology I've got right here. It's called a buffering region. So here's the definition I gave you here. It resists changes to pHs. That's what a buffer does. And we'll talk about that more in my leftovers topic right here. But that's some of the terminology I want to add to you. Eventually, this leveling effect, this buffer, eventually fails. Right? In a way, the buffer is kind of like a... Did you guys talk about buffer states in social studies? Is that a thing you ever talked about? Buffer states in social studies? I don't know. Yeah, I'll skip that part there. Another good example of a buffer would be like, right now, this chair is a buffer between me and Sam, because I don't really want to get too close to him. So I'm going to like keep a chair between us. You ever heard that phrase before? Right? That would be a good example of like a buffer in real world. And the reason why is that it leaves a little bit of a gap. It leaves some room so that, I don't know, just in case Sam wants to like punch me, he can't because I'm too far away. I don't know. I'm being dumb here. Well, that same sort of thing is kind of occurring right here. As you're adding your acid, you have a buffer. You have a little bit of room still, so to speak, because the pH still isn't changing. The pH still isn't changing. The pH still isn't changing. And if you guys can recall from like what we were doing here, here's your flask, and inside you had some base. And what you were doing is you were adding using your what was that called again? Your burette. There we go. Adding your burette, you're adding some acid a drop at a time. When does it finally change color? Well, when the base finally runs out and all of the acid has neutralized that base, then it finally changes color. Because basically what I'm saying is that base that was in the bottom there, that's kind of like the buffer concept, where you have like, you still have room left. You still have room left. You still have room left. Boom, all of a sudden it changes. And that's kind of like the little bit of space between us. Okay, so that's what I've got right here. Eventually that leveling effect, it finally fails. And so a buffer can't last indefinitely. Similarly with like, say, a hot tub, right? You put in a whole bunch of chemicals, you add those like little chlorine tablets to the hot tub, and they work for a little while, but like eventually they run out, and you have to add some more. Okay, so the inflection point or the equivalence point, then you guys hopefully know that. That's this point right here. For you guys in my calculus class, the inflection point then would be when we do second derivatives. Does that make sense? And that's where, for you guys that aren't in calculus, you'll maybe learn this one day. An inflection point, if you do like a graph, looks something like this, just so you have some context here. Right here, we have no inflection point. And the reason why is that everything here is kind of like in a downward kind of trajectory. But if I all of a sudden turn the graph around like this, that was my inflection point. And the analogy I use is it's kind of like when my daughter's on a slide. If she's going down the slide, if this is Cami going on a slide like this, and you start going down like the big drop of death like this, at some point, I kind of want the slide to all of a sudden like turn back around. Because otherwise, if it just keeps going straight down the whole time, like that's like the drop of doom. You know what I'm saying here? So an inflection point is where the graph goes from being what we call concave down to being concave up, and it kind of turns back around again. It's not actually this point right here. That point isn't an inflection point. It's this one right here. And you guys can see that on the graph. If this is the water slide of doom, drop off. But like you better actually like turn it around the other way in order to kind of end the thing. So anyways, that's called an inflection point or an equivalence point. So yeah. Okay, so let's talk a bit about indicators now. That's kind of the next little interweave topic I want to go to. When you want to try to figure out how much volume to add until your buffer fails, we call that volume the equivalence point, right? In this graph right here, it looks like you need about 24 milliliters before this buffer finally fails. The pH didn't change, the pH didn't change, the pH didn't change, and then all of a sudden, boom, it falls off a cliff. We're then looking for an indicator that's going to change color. Now, we usually used phenolphthalein, and I gave you a couple of reasons back in Chem 20 as to why. One, it's actually really easy to see the differences, because it literally goes from clear to pink. But we actually really shouldn't have used phenolphthalein. You guys know why phenolphthalein was actually a poor choice? Yeah, it's actually slightly higher than what we wanted because ideally the pH should be changing around 7, but that means that phenolphthalein is actually changing color right around here, which means that on our labs, we actually had a slight source of error. We might have been slightly off by our volume. Our volume might have been actually a drop or two too early. Can you guys kind of see how that would work on this graph? When it changed color, it probably changed color right about here, which if I drop a line down would be about there, which means we probably recorded a volume amount. You know how when you got like 12.3 milliliters every trial? You actually probably should have used 2 more drops if we used the right indicator. Bromothymol blue is actually one of the best ones because it changes color directly around the 7 mark. The only downside is, though, is that it goes from yellow to blue. And so it's not distinctive, right? Because what happens if you get kind of like a green? Do you keep going or not? You get what I'm saying? So that is one of the downsides, but you want to pick an indicator that changes color in that range there. Okay. Ideally, though, like I said, though, the pH should be about 7, but I'm going to show you the exceptions today about what happens if you're not using strong stuff. What if you start using weak acids or weak bases? Okay. So let's talk a bit about those indicators. Can you guys find your data booklets? Because I actually need to point some stuff out that's in your data books that we've probably ignored till now. I have seen this come up in, well, I've taught for 10 years now. I've seen one diploma question on this in 10 years, so this is pretty rare. Can I steal yours real quick just to show everybody? Find the table on indicators. Okay. And you probably didn't even care about this last year or recent or until now, but can you guys see how not only does it give the indicator in the pH range, but way over on the side, it gives a Ka value. We never paid attention to the Ka values because it didn't really mean anything, but now that we know more about Ka, what I need you guys to know is that indicators are actually not one thing. When we put a drop of indicator in, we're actually putting in 2 things. And that's where when you see your table there, you know how it goes like what's methyl violet? MV? Yeah, see how it goes HMV/MV negative? You were actually adding both chemicals in at the same time. Those indicators are not pure substances, they're actually mixtures. And they're mixtures of an acid and its conjugate base. And that's why they list all of those things with an H something / something without an H. And we didn't know about this at the time, but honestly, I don't think I could have explained it to you because you didn't really have the background information. So now I'm trying to explain this some more. Here's kind of the example. My board turned off. Hang on. It's been working so good recently. Seriously. Here, I'll just sit here again. Let's use phenolphthalein as an example here. What did they use for the words for phenolphthalein? It would have been H something, right? H. Phenolphthalein. HPH? Okay. So when you guys added phenolphthalein, you were actually adding HPH and you were adding pH negative. You were actually adding two compounds at the same side at the same time. One is the acid version and one is the base version. Now, what's happening between these two compounds? Well, they're playing hot potato. Because this guy has an extra hydrogen and this guy does not have the hydrogen. And if you want to use this example that I have written down here, here's what's really occurring here. This indicator right here, I'll just use HIN as the indicator, it would be reacting with water and giving its hydrogen to this guy right here and forming a little bit of hydronium. Look at the Ka values. Are they big or small? They're all actually very small, aren't they? So is this stuff here turning into this stuff very often? Well, no, it tries to. But then this guy right here, you know how this guy gives its hydrogen to water? Well, then the hydronium gives its hydrogen right back to this guy, and it goes right back to where it started from. The cool thing about indicators then is that you can actually tell the color change just like we did in our lab the other day. Remember how in our lab we had the one side was clear and the other side was like red in terms of colors? Well, these indicators, this thing right here is red and this thing right here is blue. Okay. So now think about this for a second here. Normally in an isocytic condition, what should happen here is that this thing is going to try to turn into some blue color. It's going to make a really good attempt to, right? But immediately the proton goes right back the other way. And so really you're going to have mostly red, a little bit of blue. What color is it going to end up being? Well, probably red. Does that make sense? But it's all about Le Chatelier's principle. Because let's say that then you put this thing in an acid. So let's say that you put this thing in an acid. This goes up and it shifts this way. And so when it's in an acid, it looks red. I'm sorry, we're close to it. It just comes in anyways. It's all good. Okay, but let's say that you put this thing in basic solution. Well, what ends up happening is, kind of like we did in our lab, the base is going to react with this small amount of produced acid. There's not much of this over here, but it's going to reduce with any acid that gets produced. The base would then tank this guy's concentration, and what's going to end up happening is the equilibrium would shift this way, thereby making it look blue. Does that kind of make sense? I'm going to draw this out a few more times because I want to make sure, because this is actually something that could come up. I'll use litmus as the best example. What's the abbreviation they use? Is litmus actually even on that one? Of course it's not. Let's use bromothiamyl blue then. So it's HBB. So this is bromothiamyl blue. And what you actually do when you add a drop of bromothiamyl blue is you're actually adding an equilibrium system. This is bromothiamyl blue right here, and this right here is its conjugate base. And this is the equation that's going on. Literally in that little dropper that I give you guys, there's actually an equilibrium system happening. This guy is reacting with water to turn into this stuff, but immediately it turns back. Okay. What color does it go? Is it yellow to blue? Is that bromothiamyl blue's color range? Okay. So this guy right here is yellow, and this guy right here is blue. So let's say you put this in something that is acidic. If you put this thing in something that is acidic, there might be like 99% of it on this side right here and 1% on this side right here. Right? And the reason why I'm just estimating that is because the Ka value is pretty small. Right? A Ka value tells you whether or not you expect lots of products or lots of reactants. Does the 99.1% though affect its equilibrium? No. What is equilibrium based on? That this arrow and this arrow are happening at the same rate. Okay, so do we have a lot of this stuff? Well, no. So what happens though if I add more of this by putting it in an acidic solution? Well, then it shifts it this way, which is why when it has a low pH, it should be yellow. Remember, low pHs means you have a lot of this stuff. Does that make sense? But let's say if you put it in a basic condition. So that's the opposite of this. Let's say that you put it in a pH that is high. So if the pH is high, it means that this thing right here, pH meaning high means you actually have a lot of hydroxide. Hydroxide tanks this thing's concentration. Now, was this making a lot of bromothymol blue to begin with? Well, no, it wasn't. But what you're really doing is you're speeding up the forward reaction rate because you're trying to make more hydronium. Why are you trying to make more hydronium? Well, so that the hydronium can react with the hydroxide and neutralize it. Can I say that one more time? The forward reaction rate will speed up. Okay, why is the forward reaction rate speeding up? It's trying to make more hydronium. Why is it trying to make more hydronium? So that the hydronium can then neutralize the hydroxide. But you know, as a byproduct, it then means that you make more of this stuff. And that conjugate base is blue, which is why the indicator turns blue color. Now, I've only seen this happen once, but they could ask you to do an ice chart for an indicator. It'd be rare. I've seen one of them in all my years of teaching chemistry. But because they give you a Ka value for all these things, does that make sense? You could treat this the exact same way that we treat any other question. So if I told you that you had, 0.2 moles per liter of this, you would ignore this. I could tell you that you have say you have 0 here perhaps. It goes up by x, that's an x, that goes down by x. And if I give you a Ka value of whatever it is, 1.6 times 10 to the minus 5, I'm just making up a number, we could then solve for an x value. And if we solve for the x value, see how hydronium is one of these things right here? If I solve for the hydronium amount, they could then ask you, what is the pH at that point? Does that make sense? So, anyways, I wanted to point that out. So acid-base indicators are actually equilibrium pairs, and it's all about shifts. Okay. Here's just kind of a chart kind of consolidating all the stuff we talked about then. Depending on where the pH needs to be for this to occur, depends on kind of the range. And it's kind of cool the way that we've managed to find enough indicators to really cover almost the entire spectrum. If you want to have like low pH changes, use methyl violet. You want kind of high pH changes, use like phenolphthalein or alizarin yellow. Many of them are kind of in the middle in that like 4 to 6 sort of range in there. And so that's kind of the main concept here. But you actually have an equilibrium system while you're doing like an indicator. Wait, next leftover topic. Did that make sense, by the way, before I move on to some other random thing? Because like what I just finished, this is not related to any means by. Okay, so the next topic here then is I want to talk more about polyprotic items. We've used the vocabulary polyprotic in the past. It really is like how the, suffixes of the word and the prefixes make. Poly means more than one, and protic means more than one proton. So we're looking for reactions that have the ability to react more than once. And if I've taught you guys anything in Chem 30, it's that it's a lot more complex than just A plus B turns into C plus D stop. Sometimes you need catalysts. Sometimes you need to have activation energy. Sometimes more than one reaction takes place at once. Sometimes subsequent reactions take place. And that's kind of what we're looking at here. We're looking at things that can either gain or lose more than one proton. Like, for example, where's a good one here? No, I don't have any good ones. Let me draw one out first. Like, for example, this one here. I'm trying to make it a pick. Let's do H2SO4. Because the reason why is that H2SO4 can turn into HSO4 negative. And then in a second reaction, HSO4 negative can then turn into SO4 2 negative. You get what I'm saying there? That's what makes something polyprotic. There's like two reactions taking place one after another. Okay, not at the same time. We talked about that as well there. It is possible for more than one reaction to take place at once. This is reaction 1 happens, and as soon as reaction 1 happens, another one happens right behind it. I want to show you a polyprotic base for a second, because this sometimes comes up and kids miss this one. This is not a polyprotic base. That's not polyprotic base. Because some people think, well, hang on, you just need to have more of one of something. And so they'd say, hey, look, this turned into calcium 2 plus, and it turned into 2 hydroxide. Hey, there's more than one. But did it actually happen in 2 steps? No, it just happened all in 1 step. I know you're getting double the hydroxide, but that's not actually polyprotic. Here is a good example of a polyprotic base. Okay, here's the reason why this is polyprotic. It would first dissociate into a calcium ion, and into a sulfate ion. And ionization or dissociation is pretty much happening all the time. So we don't have to worry about that part. Then what's going to happen is your sulfate will happen in the second reaction. Okay. They got muffins, yogurt, cheese, apples, oranges. Got some customers today. Thank you. See you later. Okay, so step one, I dissociated this into its two prospective ions, right? Then I took the sulfate, and I'm then going to add the sulfate to water to try to make an HSO4 negative and OH minus. Let's label the acids and bases here. Okay, hopefully it's obvious that's a base. Hopefully that's the easy one. Well, if this guy is a base, then I guess that guy better be an acid. Because they always come in like groups here. Which means that this guy right here must have been a base, and that one's an acid. And if you guys recall, like the definition, it's all about who is a proton thief and who is a proton donator. Keep in mind, no one actually really wants the protons here, though. They're hot potatoes. Water tries to give its proton over here to the sulfate ion. And when it tries to give its proton away, it makes OH minus, and then this guy has an extra proton. But unless it's something that is strong, and there's only really a few things that we know of that are considered strong, it immediately tries to give its proton right back again. That being said, will you find a couple of HSO4s just lying around in your solution at some point? Yeah. So what happens if one of those HSO4s happens to bump into a water? And this water says, hey, you take my proton too, right? This guy right here sucked up a proton from water to make this guy. It wants to give it right back away, but if another water bumps into it and says, hey, you take mine as well. It could make then H2SO4 and a second hydroxide. Now I want to point out, this reaction right here did produce two hydroxides. And this reaction right here has also produced two hydroxides. But can you guys see how it's slightly different in the mechanism? One of them required two consecutive steps to do it. This one right here, it just broke off all in one piece. So this guy right here then would be considered a polyprotic base. I mean, more specifically, it's actually this. That was the base, because what do we call the calcium? Spectator ion. The calcium was a spectator ion. Did it have to be calcium? It could have been sodium, it could have been lithium, it could have been barium. Honestly, that didn't matter. And then again, this guy right here would be a base. This would have been an acid. This would have been an acid. This would have been a base. While I'm talking about terminology, this thing right here, the HSO4 minus, we give a special name to it. And I don't know that I said it nearly as much during my last lesson, so I should really point it out right now. We call it amphiprotic. Amphiprotic, basically meaning that it has the capacity to both gain a proton and to lose a proton. And those are the ones where it can act as an acid or a base. You guys remember how in one of our last lessons we calculated Ka and Kb values? And then whichever one was higher tells you which one it is? That's the definition we call for one of these guys. If you're ever looking for an amphoteric or amphiprotic, there's another name for it, by the way. Amphoteric. There's two different names for it. What you're really looking for is anything that has a hydrogen it can give up and a negative sign. If it's a negative anion, it has the ability to accept a hydrogen. If it has a spare hydrogen lying around, it can give away a hydrogen. Anyways, this right here then describes what we call something that's polyprotic. More than one reaction in which hydrogen can transfer. Here's how this then plays in, if I kind of go back to some graphs here. When we do an acid-base titration, all I've ever had you guys do so far is a strong acid and a strong base. But what happens if I give you a polyprotic base? Can you guys see this one right here? Na2CO3. That's a polyprotic base. Hopefully you can kind of think of why. If you do this in your head, the Na and the CO3 will dissociate, and you're going to get yourself some CO3 2 negatives. Well, the CO3 2 negative can upgrade to an HCO3 negative, and then from there upgrade to an H2CO3, and then it's stuck because now it's like filled up. Does that make sense? But you know what that does to the graph? Well, it changes the graph. Now there's actually two different inflection points, because here is where it gained its first proton. And I've got kind of a reaction to show you here. This is where the HCO3 reacted with the acid, because don't forget, you're not just putting this in water, you're actually reacting this with HCl. And HCl means you've actually got H3O+. The H3O+ as an acid reacts with this base to form water and make it neutral. But hang on a sec, it's not at 7. Why is the pH not yet at 7? Why is the pH up here at 8? Because really what we've done is this acid and this base has turned into this base, and hang on, there's still some other stuff left around. Does that make sense? Now, I know I wrote this guy as an acid, right? This acid and this base turned into this base and this acid. But this thing right here, is it just an acid? Well, no, it also can act as a base and react a second time, which is why the pH isn't quite down to 7 yet. It's more like at 8 right here. Because now a second reaction is going to take place on this slide here, and that's at this equivalent point. The HCO3 reacts with more acid, produces more water, and this guy right here. And now what we've got is the same thing. This acid and this base forms this base and this acid. And this one right here, can this guy continue to react? No, it's kind of stuck. Why can't it pick up any more hydrogens? What would it need to pick up hydrogens? Yeah, it'd be negative charged, right? And this guy's now full. Right? So now this kind of makes sense. Now we're producing acid, which is why the pH down here is so low, because now you finally started to produce acid, and this acid's not going to subsequently react anymore. So the further this goes, we now get that buffering region. If you keep adding more and more and more of your titrant, if you keep adding more and more and more of this stuff here as your titrant, eventually the pH is going to only have produced acid, and really the pH won't really change anymore because it's so low it can't get any lower. Does that make sense? So I need you guys to be able to recognize a graph and kind of just figure out whether or not it is a monoprotic acid versus a diprotic acid versus a triprotic acid. That's as far as it goes, by the way. Anybody think of a triprotic acid? Yeah. Yeah. H3PO4 is the only tri one I know of. Right? Many things are diprotic. Even oxalate will do that, by the way. Like there's HOOCCOOH, and you can actually rip off 2 different hydrogens. Okay. So we can have a lot of things that are mono, di, or tri, and they just give extra little, I don't know, like kind of inflection points along the way. Basically what I need you guys to be able to do is look at a graph and interpret what is happening, and make an assumption as to, well, what sort of possibilities could there be? This graph right here could not have been HCl plus NaOH. That is not possible. Okay. This graph, though, could have been HCl plus BaCO3. This graph also could have been H2SO4 plus NaOH. Because this guy right here has 2 different reactions that could take place. See what I mean? This graph also could have been HOOCCOOH and NaOH. Because again, this guy has 2 different points it could have reacted at. I think I kind of talked about all the stuff I wanted to there. This just kind of goes through all the reactions that take place. Like this is the first reaction. The CO3 bumps up to HCO3. And then here the HCO3 bumps up to the H2CO3, and now we're done. So I don't know that you guys can read through whatever's there, but I've kind of covered the basics. What I did need you guys to know though is when a strong base reacts, there is only one strong base. There are 6 strong acids, but the one strong base is anything that is an OH minus. Okay. Which is why when we have like say NaOH and you try to dissociate it into Na plus and OH minus, it does not go back. Okay. Anything strong for bases is anything NaOH. Okay. What I do need you guys to be able to do though is if it's polyprotic, you should be able to apply Hess's law to this. You guys remember Hess's law from way back when in like, I don't know, February? The basic idea is here's your first reaction where the CO3 upgraded to an HCO3. Here the HCO3 upgraded to an H2CO3. In theory, then you guys should be able to like cancel this one on that side there. You should be able to say you now have two of these. You should be able to say that you now have two of these. This guy goes there and that guy goes there. So you could, in theory, like make a net overall reaction. So you should be able to recognize that. We may even write it with the spectator ions as well then too, because this CO3, it actually started as a, where did we start here again? It was an NaCO3. So like you could even write the equation like this, where this CO3 right here, I've re-added the NAs to it again. And this H3O right here, it really came from HCl. The HCl broke up into H3O plus and Cl minus, but I've been ignoring the Cl minus the whole time. So you might even see it written like this. So this would also be another way of writing more or less the exact same thing. Does that make sense? So that's polyprotic acids and bases. One more thing about polyprotics. They have more than one Ka value then, because there's more than one reaction taking place. There's the first and second and possibly even third reactions. If you guys could take a look at that indicator table there, there's actually a couple of polyprotic indicators. The first one that I know of is the Kresgal red. Can you guys see how Kresgal red actually goes from H2Cr to HCr minus, and then from HCr minus to Cr2 minus? There's actually two different Ka values. So you do got to be careful that if you ever work with something polyprotic, make sure you use the right Ka value. The first one, the second one, or maybe even the third one. Because this is for when it loses its first hydrogen. This is for when it loses its second hydrogen. And can you see how ascorbic acid has two hydrogens that it can lose? Carbonic acid also has two hydrogens it can lose. Citric actually has three. So make sure you're careful about which Ka value to use. Okay, next leftover topic. I didn't fully explain your pH curves probably back in grade 11 as well as I should have. But again, we hadn't really talked about strong and weak acids and bases. So really the only graph I've shown you so far is the one in blue right here, where you start with a strong acid and you get a strong base. And the curve is like a really, really sharp S-looking curve. It's really flat, then it all of a sudden spikes, and then it flattens off again. But the truth is that's actually only true for strong acids and strong bases. What happens if we add weak acids and weak bases? Well, it changes the graph a bit. For example, what happens if we use a weak acid? A weak acid actually wouldn't be quite as low as a strong acid. I need to talk about why for a second here. A strong acid would be something like HCl. And HCl would react with water, and it would form Cl minus, and it would form H3O plus. But, like I've been joking around the whole time here, what makes it strong is its ability to not get back together again. And so it does not have a backwards arrow, which means you have lots of H3O plus. And if you have lots of H3O plus, what does it mean about your pH? Very low. However, let's do the exact same thing with a weak acid. Like, for example, HCOOH. This is formic acid. Formic acid undergoes almost the exact same process. Turns into COOH, oops, that's too many O's, COOH minus, and H3O plus. Hey, it also produces hydronium, except it's weak. It gets back together again. So do you have as much H3O plus as you were expecting? Well, no. And can you guys see how this green little line right here, if you have a weak acid, the pH actually starts a little bit higher. And the graph shape isn't actually quite so flat across. It actually starts a little bit higher, does a little curve there. And you know what else happens? The pH inflection point of the graph actually ends up being a little bit higher. It's actually not at 7 anymore. If you have a strong acid and a strong base, it's actually at 7. But what ends up happening is you weren't really making very much hydronium. And so when you react that with lots of hydroxide, it's not an equal balance. Rather than there being all of this and all of this, where it neutralizes right at 7, there's only some of this to react with all of this. Does that make sense? And so what you really have is a little more hydroxide than you have hydronium because of the fact that you used a weak acid. So you actually get an inflection point that's slightly above 7. And that same logic applies if you were to say to use a strong acid but use a weak base. If you use a strong acid and a weak base, it actually means your inflection point might be a little bit below 7. So I think I've got pictures on the next few slides here. Yeah, I do. So let's say you have strong acid, strong base. This is what I've shown you up till now, so this really hasn't changed. But you have everything's producing hydroxide. Everything's producing hydronium. It should even out perfectly. And so therefore your pH equivalence point, your endpoint should be right at 7. Whether or not you're going in the upwards or downwards trajectory, it should be at 7. However, what happens if we were to use a strong acid and a weak base? So let's write one of these ones out. Let's say that I were to use, well, I guess this one works here, although that's not a weak base, so I don't know why they use that one. Let's use NH3 instead. NH3 is a weak base. NH3 tries to react with water and tries to turn into OH minus and NH4 plus. It tries to. It really does its best. But it turns back to where it started from. So based on that, if we have these two reactions taking place, HCl and water is completely turning into hydronium and Cl minus. You're going to have lots of hydronium because all of this turns into this guy here. But when you use a weak base, this guy tries to react with, it tries to turn into hydroxide, but does it stay that way? No. So I guess what I'm trying to say is you have lots of this, you have some of this. Who ends up winning the fight? Well, there's more hydronium. And so what ends up happening is your equivalence point is sometimes actually a little bit lower than 7. Here's a weak acid and a strong base. This is actually where phenolphthalein becomes the greatest indicator in the world. Because you know how I kind of told you a little while ago that phenolphthalein, we kind of cheat a little bit with it? Well, if I ever give you a weak base and a strong acid, which I actually didn't. I always gave you guys strong acids and strong bases. But if you're ever using a weak acid with a strong base, then what should happen is the equivalence point should actually get pulled up a little bit. And this is perfect then, because then it's right in phenolphtalene's wheelhouse. So most of the titrations we try to use, we actually try to use a strong base, like say NaOH, but then we try to use a weak acid. And if we use a weak acid, then it pulls the pH up a little bit. And then actually phenolphthalene's the exact right indicator to use. So what I need for you guys to be able to do then, I'll try to make up a pretend diploma question, is they like to do this numeric response-wise. They'd give you 4 graphs. So I'll just say like 1, 2, 3, and 4. I'll just draw 4 graphs out here. So like here's 1. Here's 2. Here's 3. Here's 4. And then if it were to give you like, say, I don't know, 4 different blurbs here, just make one up. This one would be HCOOH plus NaOH. This would be HCl plus CaOH2. Let's see, let's do NH3 plus HCl. Oh, I've really done the same graph twice, actually, haven't I? Let's just get rid of that one then. Okay, could you guys match the graph to the letter then? Which one is going to be the CHOOH plus NaOH? Oh, hang on, that's not right either. Hang on. Let's make this one HCCOCCH. Is that the right one? Yeah. Choose that one. Which one is this plus NaOH going to be? That'll be 3. Here's the reason why. I started with an acid, and then the acid started low. I ripped off 1 proton. That's this equivalence point right here. I then ripped off the second proton. That's the equivalence point right here. And because I was adding NaOH to it, I finished with a high pH. Follow that? This one right here is meant to be a strong acid and a strong base. So here is a strong acid. Here is a strong base. I also meant to fool you here. Is this actually polyprotic? No. Just because there's OH2 doesn't actually make it not polyprotic. So this would be a strong acid, and I added a strong base to it, so that would have been this one. This one right here would be starting with a weak base and finishing with a strong acid. So see how I left this guy ending up really high? I actually started this one a little bit lower because this is actually a weak base, and as I added a strong acid to it, the equivalence point would have been, this would have been 7, it might have been closer to 6, because this is a weak base and a strong acid. Does that kind of make sense what I'm trying to get at? So they'll ask you basically a question where there's going to be different shapes of graphs, and you have to figure out whether it's strong or weak, and whether or not it's polyprotic or not. And then you should also be able to figure out whether it's going from acid to base or from base to acid. Basically, if it goes from low to high, you're adding a base. If it goes from high to low, you're adding an acid. I should add one more thing, by the way. You actually can't do a titration with weak acids and weak bases. Anyone want to hazard a guess as to why if I didn't write on here? Oh, I guess I kind of wrote on there. Why would a titration not work with a weak acid and a weak base? No, they have no capacity to neutralize each other. Nothing would occur. Here's the reason why. If this reaction never, like A tries to turn into B, but it turns right back again, it doesn't actually make any products to work with. And if the other reaction also doesn't really make any products to work with, there's really nothing to neutralize. Does that make sense? Like, maybe try to draw this one out again. You have an acid, and the acid tries to turn into a hydronium, but really it just turns right back again. And you have a base, and a base tries to turn into a hydroxide, but it turns right back again. Do you have some of this stuff here? Well, yeah, I guess you have some, but you really didn't make very much, because remember, most of these weak things, it happens like, 2% of the time, right? Their Ka values are so ridiculously low. And so what ends up happening is you get a graph where, yeah, the pH will eventually change, but like there's hardly any like distinctive point. You might find a point here, but like it's almost like it's a straight line. And so we can never actually do weak acids and weak bases. They just don't really work all that well. It's not very sharp, so to speak. So you should be able to do strong acid, strong base, strong acid, weak base, weak acid, strong base, anything polyprotic. You should be able to look at those graphs and kind of tell me approximately what's going on. Yeah, here's kind of like the summary slide. So strong acid, strong base is a nice sharp point right at 7. Strong acid, weak base drops the initial value, so it's actually got a low pH. Weak acid, strong base actually increases it, and this is like almost like a straight line. Because like there's nothing there to react. Nothing actually got formed. Yeah. You'd have to look at the shape of the graph. Like since it says, I guess they'd have to somehow. Yeah, they'd have to tell you somehow as to what the titrant is and what the sample is. Based on this one, because it says it's the volume of acid added, then I know that we're starting with base and dropping down to acid. You know what? I would have to have changed this and saying that this start with this and add this. I'd have to like phrase that somehow. That's a good point, because honestly, these two things right here, it would actually be the exact opposite if you started with this and added this. Good question. Okay, last leftover. So again, just kind of like putting all my random stuff together here. I want to talk a little bit more then about that buffer concept. So a buffer then involves anything that resists a pH change. Okay. And again, I mentioned earlier in class, buffers would be in things like, say, your blood system, or your stomach probably has a buffer in order to make sure that it maintains its acidity. Because like what happens if your stomach lost its ability to be acidic? Well, then you wouldn't be able to digest food properly, right? So hot tubs is the other example I would give here. So in order to create a buffer then, what you have to have is this. You have to have a weak acid and its conjugate base. Let me try to explain how this is going to work before I go on in my notes here. Let's say that you have a weak acid. I'll use acetic acid, CH3COOH. Okay. And let's say that it's almost just like we talked about with our indicators, where I'm also going to add in an equal amount of CH3COO negative. Let's say I put in a whole bunch of both of these into a system. What's going to happen between these two guys right here? Are they going to react with each other? Yeah. Because you know what's going to happen is this guy right here is going to try to give its proton to that guy, who then is going to try to give it back again, who's then going to try to give it to this one right here, right? I mean, really what you're going to have, if I draw it with, like, say, water, is you're going to have CH3COOH reacting with water to form CH3COO minus and, let's say, H3O plus. And really, the protons are just bouncing back and forth between there. Okay. Now, here's the great thing about a buffer. This is the one time where, you know how I've been saying equilibrium doesn't mean you have 50% on both sides? Well, actually, now you're going to want to do that. Let's try to make about half of it this stuff here, and about half of it this stuff here. Because here's what happens. Let's say that you add some acid. Hypothetically, you add some acid. Well, you know what can end up happening is this acid right here can be neutralized because this guy right here can pick up the excess protons and turn into that stuff right there. And what ends up happening is the pH doesn't change all that much because this guy has the capacity to steal the extra protons that have been added into the solution. And so it really doesn't change pH all that much until you run out of this. As soon as you run out of this, because remember, this is going to cause the reaction to shift that way, as soon as this conjugate base, you run out of it, just like in our titrations, you know how the color changes when you run out? Well, the same thing would happen here. Then your buffer would fail, and as you keep adding more of this, well, eventually the pH will change. However, let's say you're adding a base. Oh, I didn't mean to do that. Did I undo that? Good. Hold on, just erase this. Let's say you're adding a base. What would happen if you added a base? Well, if you added a base, you're really decreasing this guy's concentration. How are you decreasing this guy's concentration? Well, because the forward reaction rate is going to take place more often. Because you know what's really happening when you're adding your base is taking this guy's proton away from it. And you're saying, hey, I've got a base. I'll take this guy's proton here. Now that works great until you finally run out of this stuff right here. What happens when you finally run out of this stuff right here? Well, then you don't have anything more to work with, and eventually the pH will change as well. So the basic concept is you want to have a 50-50 spread of both an acid and its conjugate base. You want to have about an equal amount of both so that it can protect against proton gainage and proton lossage. This guy right here can absorb extra protons if you add acids. This guy right here can give away protons if you add extra bases. The only problem is eventually one of these two things you'll run out of, and then the buffer fails. And that's kind of what's happening in this graph right here. Right here, what we've got going on here is we took an acid, like say acetic acid, and so acetic acid would have been CH3COOH. And as we add NaOH to it, you know what we're forming is some CH3COO negative. Because really, that's what this guy's turning into. This guy and the base is turning into this thing right here. It's losing its proton. This base right here is stealing that guy's proton. But at this point right here, we still have some of this, and we're making some of this. So we have a buffer sitting right here. Why does the buffer fail right here? Well, because eventually I run out of acetic acid. And as soon as I run out of acetic acid, now the pH has to change. Makes sense? I've got some slides kind of talking about that, but this is kind of the picture I want to end with then. The acetic acid buffer then has the ability to add to NaOH. Because really what you've got is your CH3COOH and you've got your CH3COO negative. As you add your NaOH, what's happening? Well, the OH right here wants to steal a proton. Who has a proton? You do. Specifically this proton right here. And so the OH tries to steal this guy's proton. And the pH will stay the same until finally all of this runs out. And then if there's no more protons left to steal, then this base right here causes the pH to increase. But let's say you're adding HCl. Well, HCl actually wants to give its proton to somebody. Now, can this guy accept the proton? No, but that's why you have to have a weak acid and its conjugate base so that this guy can accept the proton. But eventually, all of these guys right here will react and accept protons, and then at some point, we keep shoving more and more hydrogens in there. And so this guy takes a hydrogen, and the next guy takes a hydrogen, and the next guy takes a hydrogen, and eventually there's nobody left to take hydrogens, and what happens to the pH? Well, the pH falls. So this is actually a really easy question normally on the diploma. What they'll do is they'll ask you, which of the following is a buffer? So, like here's a good example of one. If I give you CH3COOH and NaOH, that's not going to work. But if I give you CH3COOH and I give you NaCH3COO, that one's a buffer. And the reason why is that this guy is a weak acid, and if you kind of ignore the sodium part of it over here, this guy right here is a conjugate base. It has to be its conjugate base, by the way. The reason it can't be just some other random base, it can't be CH3COO negative and NH3. The reason why is that this would actually react with that one. And we don't want this guy to lose its proton to that one because we need this guy to keep its proton in case you add some other base. Can I say that one more time? It has to be a weak acid and its conjugate base because this guy and this guy, they can keep doing the proton flip as long as you want. No big deal. But if you add this acid right here and some other random conjugate base, well, the whole point of this is that I want to have an extra proton sitting here in case I need it to neutralize a base. But you know what this guy's going to do? It's going to literally neutralize that base, which means you don't have the proton left to neutralize the other base that's coming in the future. You get what I'm saying? So here's another good example of one. HCl plus NaCl. That doesn't work because HCl is a strong acid. And strong acids have already given away their protons. Right? You need somebody who's weak because the weak thing tries to give away its proton, but like because it's weak, it comes right back again. So this guy's no good because, well, his proton's already going to be missing. So one more example then would be like, say, if I gave you NH4 plus and NH3. That would work because this is a weak acid and this is its conjugate base. If I add an acid, this guy right here can steal the acid's proton. If I add a base, this guy right here can donate a proton, which is why you want about a 50-50 split. It's the one time you actually want it 50-50, because that way you have equal protection against both possibilities. And so there's a lot of known buffer systems. Like you guys apparently have learned about this in biology. So that's all I got. Questions? Okay, so here's where I go from here then. This last unit, minus this little leftover section, really consists of about maybe three main things. The first is Le Chatelier's principle. You guys have to know the idea of if you increase, it shifts this way, or if you decrease, it shifts this way, all that sort of stuff. That's one concept you need to know. Second concept is you have to be really good at using your ice charts and your K values. And if I give you data that goes into a chart, you should be able to calculate a Kc value, or if I give you a Kc value, you should be able to like reverse engineer that, possibly using the quadratic formula, possibly. Okay, that's the second thing. The third one, what was I going to say again there? The third one is kind of like all the theory behind the idea of who's an acid, who's a base, who is losing a proton, who is gaining a proton. What is a conjugate acid, conjugate base? A lot of it is like naming type theory type stuff. Okay, those are kind of the three main things for you guys to do. If you guys haven't finished your first quiz, do that as soon as you can. I got to point out though, the only thing that's not on that first quiz though is I didn't actually specifically make it about Ka values. So what I'd like to do going forward, I guess, is next week we'll do a quiz on Monday and we'll do our unit test on Wednesday, if that still works for you guys. And then that gives us basically 3 solid weeks to get ready for our diploma. So, sound good? Okay, let me know how I can help with stuff then.